Late November 1944. A freezing rain falls steadily over a muddy, swollen river somewhere near the German border. The 30-ton tank slews sideways, grinding to an immediate, metallic halt. Smoke begins to pour from the engine deck. If the tank's number was higher, the tracks stopped. There was no debate. There were no radio calls to higher headquarters for permission. The yellow circles stripped away the friction of command decision and replaced it with strict, visual math. Back in the freezing rain at the river crossing, this mathematical doctrine is the only thing preventing a structural catastrophe. The American armor commander sitting in the tree line does not need to guess whether a rescue attempt will collapse the bridge. He looks at the yellow sign hammered into the earth near the approach road. It reads 40. He knows the disabled Sherman bleeding smoke on the center of the span is a Class 30. The math instantly dictates the physical reality of the ambush. The bridge can withstand an MLC of 40. The dead tank already consumes 30 points of that allowance. The margin of structural safety is terrifyingly narrow. If the commander sends another Class 30 combat tank onto the span to push or pull, the combined load immediately hits 60. The structure will fail, and the crossing will be lost. But this strict limitation was exactly what the mechanical recovery system was built to exploit. The Army did not just standardize the math, they standardized the machines required to solve it. The crew bails out over the sides, splashing into the freezing river below. The German gunner exhales. He has done his job perfectly. The commander knew he had a mathematical remainder on the bridge's tolerance. He just needed a vehicle that fit inside that narrow remaining window, yet possessed enough raw mechanical power to drag a locked steel anchor backward. The yellow sign hammered into the mud reads 40. The disabled Sherman bleeding smoke on the center of the span is a Class 30. For the American armor commander watching from the tree line, this simple subtraction problem dictates the entire tactical geometry of the rescue. The math is absolute, and the margin of safety is terrifyingly narrow. If the commander sends a heavy armored recovery vehicle rolling out to the center of the bridge to tow the wreckage directly, he instantly violates the structural law of the choke point. A standard medium recovery vehicle weighs roughly 30 tons. Adding that mass to the dead, Sherman creates a combined, localized live load of 60 on a span rated for 40. The moment the rescuing tracks meet the wreckage, the timber decking will shatter, the girders will buckle, and both machines will drop into the river. The military load classification system did not merely restrict forward movement. It dictated the physical method of recovery. Because the math forbade the rescue vehicle from sharing the weakened center span with the casualty, the commander had, by the established laws of physics and armored warfare, he has just won his battalion hours of time to execute a standoff extraction. The rescuing machine could not drive to the tank, it had to reach it. This is why the recovery vehicle that breaks from the tree line does not blindly charge onto the wooden planks. It advances only as far as the stone abutment at the very edge of the crossing. Here, on the solid, compacted earth of the approach road, the weight limit is effectively infinite. The vehicle stops. It violently slews its tracks, digging its steel grouses deep into the freezing mud to form a mechanical anchor. The crew scrambles over the steel hull, completely exposed to the freezing rain and the imminent threat of pre-sighted artillery. They begin stripping heavy, inch-thick braided steel cable from a massive internal drum. Sliding and stumbling, they drag this heavy line on foot across the slick, exposed surface of the bridge, hooking it securely to the reinforced towing pintles on the rear of the dead Sherman. By using the cable, the recovery crew isolates the burden. They have successfully removed the weight of their own vehicle from the bridge's structural equation. The fragile span now only has to support the 30 tons of the disabled tank. The vertical math is balanced, but solving the weight limit immediately introduces a new, equally violent physical problem: horizontal friction. A tank with a shattered track and 30 tons of dead steel now block the only crossing. Behind the smoking Sherman, the rest of the armored column slams on its brakes. A locked final drive does not want to roll. It wants to dig. When the cable pulls taut, the disabled Sherman will act, like a massive steel plow scraping across the bridge's timber decking. The sheer mechanical force required to break that static friction and drag a locked 30-ton iron box backward through the rain is immense. If a standard combat tank attempted to pull that cable, the physics would immediately work against it. A standard tank is relatively light for its engine power, designed to move quickly and smoothly over soft ground. If a standard Sherman tries to drag a locked dead weight equal to its own mass, it will not pull the wreckage backward. Instead, the rescuer will simply drag itself forward. Its tracks will spin uselessly in the mud, eventually slipping over the embankment and into the water. To pull the dead weight without breaking the bridge or dragging itself into the river, the army needed a vehicle that defied the standard rules of armored warfare. It had to be heavy enough to anchor itself against the pull of a locked tank, yet geared low enough to multiply the torque of its engine into pure pulling power. The cable was attached. The structural math was solved. Now, everything depended on the strange, turretless machine waiting at the bridgehead. A dozen tanks, half-tracks, and supply trucks are suddenly stacked nose to tail on the narrow approach road. They are completely exposed. The machine idling on the muddy approach road is an M32 armored recovery vehicle. To an untrained observer across the river, it looks like a standard Sherman tank that has been violently decapitated. The heavy rotating turret, the main 75mm gun, and the internal ammunition racks are entirely gone. In their place is a fixed, open-topped superstructure. A massive steel A-frame boom rests flat against the hull, and the exterior is heavily cluttered with spare road wheels, oxy-acetylene welding tanks, heavy steel blocks, and pry bars. It is an armored surgeon, stripped of its ability to kill and rebuilt entirely to save. As the freezing rain slicks the armor, the M32 crew prepares to solve the friction problem that would easily drag a normal combat tank into the river. They do this by severing the connection between their engine and their tracks. Inside the cavernous hull, occupying the space where the turret basket once rotated, sits the true weapon of the recovery unit. It is a massive Gar wood winch, spooled with hundreds of feet of thick, braided steel cable. The driver shifts a heavy lever, engaging a power takeoff unit. The roaring radial engine behind him no longer attempts to spin the drive sprockets. The steel tracks remain completely motionless. This is the defender's dream. In standard tactical doctrine, a bridgehead traffic jam is a graveyard. Instead, the total mechanical output of the engine is diverted directly into the winch drum. This single mechanical alteration transforms the entire physical geometry of the vehicle. It is no longer a tank trying to find traction in the slick mud. It has become a stationary, armored capstan, capable of exerting 60,000 pounds of direct pulling force. If that immense force is still not enough to break the locked, static friction of the dead Sherman on the bridge, the crew does not simply rev the engine harder. They use mathematical multipliers. Working exposed in the rain, the mechanics rig heavy steel snatch blocks into the cable line. By threading the winch cable through these specialized pulleys and anchoring it back to the recovery vehicle, they halve the speed of the pull but instantly double the torque. This system allows a single machine to slowly drag, a dead weight vastly heavier than itself, without stressing the engine to the point of catastrophic failure. But immense force always demands an equal and opposite reaction. If the winch pulls with 60,000 pounds of tension, that same force is simultaneously pulling the M32 forward toward the edge of the chasm, to prevent the rescuer from being dragged onto the fragile span. Within minutes, pre-planned German artillery should begin raining down on the trapped vehicles. The attacking force has lost its momentum, its mobility, and its initiative. And violating the structural math, the recovery crew employs a brutal, unyielding solution. They drop massive, spiked steel wheel chocks and spades directly in front of the tracks. As the winch begins to turn and the cable pulls taut, the M32 violently slides forward a few inches. The heavy steel spikes drive deep into the compacted earth of the riverbank. The terrain compresses under the tracks. The recovery vehicle locks solidly against the geography itself. The artillery spotter across the river is finalizing his coordinates. The tactical delay brought by the German anti-tank gun is evaporating. Inside the hull of the M32, the winch operator watches the heavy steel line rise from the mud, shedding freezing water as it tightens into a rigid, trembling bar. The engine note deepens to a heavy, labored growl. The machine has mathematically balanced the bridge capacity and safely anchored itself to the earth. Now, it must execute the exact, brutal choreography required to break the grip of the shattered tank. The braided steel cable vibrates in the freezing rain. Inside the hull of the M32, the radial engine screams at maximum output, but the tracks remain perfectly still. All that mechanical violence is channeled directly into the heavy winch drum. Out on the center of the span, the disabled Sherman groans. The American commander cannot simply order the second tank in line to ram the wreckage forward. It is 30 tons of dead iron, its broken track locked solid against the timber decking. The physical resistance is immense. For a long, agonizing second, nothing moves. The bridge shudders. Then, the raw, multiplied torque of the Garwood winch overcomes the laws of static friction. With a deafening screech of tearing wood and grinding steel, the dead tank lurches backward. It does not roll gracefully. It is dragged. The locked track acts like a massive steel plow, scraping violently across the bridge surface. Splinters of wet timber and sparks shower from the chassis. Inside the M32, the winch operator watches the drum carefully, maintaining a steady, unrelenting pull. He is managing a terrifying balance. If he yanks the casualty too aggressively, the sudden shock load will snap the steel cable, whipping it back toward the recovery vehicle with enough force to cut a man in half. If he pulls too slowly, the German artillery spotter across the river will finish his calculations, and the incoming barrage will annihilate the entire trapped column. The mathematical geometry of the extraction holds perfectly, because the M32 remains anchored on the solid embankment. The fragile center span is never forced to bear the combined live load of the two machines. The bridge groans under the proper, sliding friction, but its structural limit is never breached. Foot by foot, the smoking wreckage is dragged backward off the weakened timber decking. Pushing a 30-ton dead weight with locked treads across a rain-slicked bridge is a mechanical nightmare. And onto the compacted earth of the approach road. The moment the casualty clears the bridge abutment, the choreography instantly shifts. The winch stops. The M32 crew leaps out into the freezing rain, abandoning the safety of their armored hull. They hammer the heavy steel pins out of its end, the tow shackles, and drop the rigid cable into the mud. The M32 driver immediately disengages the power takeoff and reconnects the engine to his tracks. The recovery vehicle pivots, drops its heavy steel nose against the side of the shattered Sherman, and violently shoves it off the roadbed and down into a muddy drainage ditch. The choke point is broken. The entire operation, from the moment the track snapped to the moment the road was cleared, has taken a matter of minutes. The American armor commander in the tree line throws his arm forward. Engines roar down the length of the column. The remaining Shermans throttle up and surge across the intact bridge without slowing down. Less than 2 minutes. Later, the first heavy German artillery shells scream out of the sky. They detonate violently in the mud along the approach road, cratering the exact spots where the trapped vehicles had been parked. But the shells are hitting empty ground. The artillery is bombarding a ghost. Across the river, the German anti-tank gunner lowers his optic in disbelief. He has witnessed a localized tactical defeat, but he is actually looking. It destroys transmissions and shreds the tracks of the pushing vehicle. Worse, sending more armor onto a damaged, heavily loaded span invites a catastrophic structural collapse. At a strategic catastrophe, he successfully disabled a combat tank, but he could not disable the logistical system behind it. The Americans did not just bring armor to Europe. They brought an integrated, mechanized network designed specifically to absorb and erase battlefield friction. The German military possessed brilliant engineers, thicker armor, and terrifyingly powerful guns. But they lacked this seamless integration of math and recovery doctrine. When their own massive vehicles broke down on a narrow bridge, their crews faced a fundamentally different reality. To understand the sheer strategic advantage of the American recovery network, you must look at what happened when the exact same battlefield friction struck the opposing force. Imagine a similar stone bridge, 50 miles away, carrying a German heavy armored column. This time, the lead vehicle is a Tiger tank. It does not even take an enemy shell to paralyze the advance. As the behemoth crawls across the span, its overstressed final drive simply shatters under the 56-ton weight of the machine. The tracks lock with a sickening crunch of sheared metal. The tank dies right in the center of the crossing. The German commander now faces a mathematical and mechanical nightmare. German engineering produced terrifyingly lethal combat vehicles, but it severely neglected the logistical ecosystem required to sustain them under stress. The German army lacked a unified, instantly readable equivalent to the yellow military load classification circle. Hidden inside a camouflage position on the eastern embankment, a German anti-tank crew waits behind the breech of a 75mm PaK-40 gun. The attacker is paralyzed, or at least they should be. The German gunner watches through his optic, waiting for the panic. More importantly, they lacked abundant, standardized recovery vehicles paired specifically to the weight of their own armor. A Tiger is nearly twice the weight of a Sherman. To move a locked 56-ton dead weight, German recovery doctrine often relied on tying 3 massive SD, KFZ, 9 FAMO half-tracks together in a cumbersome chain. The physical reality of the choke point makes this impossible. 3 18-ton half-tracks plus a dead 56-ton tank creates a localized load of over 110 tons. If they attempt the rescue, the rural European bridge will instantly disintegrate. Even if the German column possessed a specialized Bergepanther recovery tank, the extraction would not happen in minutes. The rigging was incredibly complex. The heavy steel tow bars required for the massive weight took exhausting labor to assemble. Worse, these specialized recovery vehicles were not intimately integrated into every forward assault column. They were scarce assets, often hoarded by higher command echelons miles to the rear. There was no standardized doctrine for a rapid, standoff winch extraction under direct fire. Instead of a 2-minute delay, the breakdown becomes an operational catastrophe. The trapped German column cannot move forward. They cannot physically push the iron behemoth. As Allied fighter bombers begin circling overhead, drawn to the static traffic jam, The German commander loses all his options. He is forced to order his crew to plant demolition charges inside the hull. They detonate their own engineering masterpiece, leaving a shattered, burning barricade permanently wedged across the bridge. The armored advance is dead. He waits for the Americans to abandon their vehicles and run for the tree line. Instead, something entirely different happens. This was the invisible vulnerability of the heavy armor philosophy. The German military built mechanical fortresses, but a fortress that cannot be moved becomes a prison. The American military took a completely different approach. They accepted that tanks would break, burn, and be disabled. They did not try to build an immortal vehicle. They built a highly resilient system. The Sherman was deliberately designed to be lighter, strictly adhering to load classifications, specifically so it could be rapidly towed, repaired, and replaced by the matching M32 recovery vehicles that followed right behind it. The enemy could clearly see the sheer number of Allied tanks swarming across Europe. What they could not see was the math painted on the fenders, or the doctrine that kept that armor moving through impossible bottlenecks. But a system is only a theory until human beings execute it. The math worked, the machines worked. Yet, translating that mechanical choreography into a battlefield reality required a very specific type of soldier. The cost of keeping the armored columns rolling did not fall on the generals who designed the load classifications. It fell entirely on a handful of men who had to step outside the safety of their armor. The freezing rain continues to fall over the swollen river. The smoke is still clearing from the center of the span, but the timber decking is empty. The American column does not retreat. The vehicles do not scatter. Within a remarkably short window of time, a strange, turretless vehicle breaks from the tree line. For the German gunner watching from the eastern embankment, the reality is difficult to accept. He executed a flawless ambush. He hit the correct target at the perfect choke point. Yet, the American column is already disappearing into the tree line, leaving him with a tactical victory that achieved absolutely nothing. The question was never really about how a single disabled Sherman was cleared from a rural crossing. It was about two colliding philosophies of war. The German military built mechanical masterpieces designed to dominate individual engagements. The American military built a resilient, continent-spanning system designed to absorb friction and maintain constant forward motion. That system was bound together by the yellow military load classification circle painted on the fenders, the rigid structural math of the combat engineers, and the massive torque of the Garwood winch. But equations and machines do not win wars. They only create the potential for victory. Translating that mathematical potential into a physical reality required a very specific type of soldier. The armored recovery crews occupied a unique and terrifying space in the architecture of the conflict. A combat tank crew fought, buttoned up behind inches of sloped steel. An infantryman under fire could dive into a crater or take cover in a ruined cellar, and rolls directly onto the bridge. There is no chaotic ramming. There is no structural collapse. Heavy cables are pulled. Winches grind. The crew of an M32 armored recovery vehicle had no such luxury. Their job fundamentally required them to drive directly to the exact point of maximum danger, the blocked intersection, the mined road, the pre-sighted bridgehead, and then step outside. To rig a standoff extraction, a mechanic had to leave the armored hull. He had to stand completely exposed in the freezing rain, slipping on the muddy approach road. He had to wrestle with thick, braided steel cables coated in heavy grease and freezing water. He had to lift heavy steel snatch blocks and hammer iron pins into towing shackles while sniper rounds cracked overhead and mortar shells began to walk closer. If the winch cable snapped under the immense tension, it would whip back with enough force to cut a man in half. If the load calculation was wrong and the bridge gave way, he would go down into the river with the wreckage. These crews performed heavy industrial labor in the middle of a firefight, communicating only through frantic hand signals over the deafening roar of the radial engine. These men were rarely mentioned in the newspaper dispatches. There were no propaganda posters celebrating the mechanics who dragged dead steel through the mud, or the combat engineers who measured timber decking under fire. Yet, without their unglamorous labor, and then, seamlessly, the massive steel roadblock is dragged backward and shoved off the embankment. The bridge is clear. The greatest mechanized armada in history would have suffocated under the weight of its own casualties. Every shattered drive sprocket, every snapped track, and every burned-out hull would have become a permanent barricade. Instead, the dead vehicles were dragged into the ditches. The fragile bridges held. The columns kept moving. By the time the cold sun finally rises over the river, the front line has already advanced miles to the east. The only evidence that the ambush ever happened is a scarred Sherman resting quietly in a drainage ditch, and the deep, violent gouges carved into the earth by the steel anchor spades of a machine that simply pulled the roadblock away. The surviving Sherman crews throttle up, and the assault rolls forward as if the delay never happened. The German gunner is left staring at an empty bridge. His calculation was flawless, yet his tactical victory evaporated in minutes. He witnessed a recovery, but he could not see the massive, invisible framework that made it possible. This was not just a lucky tow cable or a brave rescue crew. To understand why this immovable roadblock disappeared so quickly, we first need to understand the invisible physics of a dead tank. A killed vehicle does not just stop moving, it actively fights the earth beneath it, transforming into an anchor that defies brute force. The gunner presses his eye against the optic. His target is a narrow stone and steel bridge, its surface slick with rain and mud. A 30-ton tank in motion is a surprisingly graceful machine. Its weight is distributed evenly across a long line of road wheels, while the tracks act as a continuous, self-laying road. As long as the engine runs and the transmission engages, it requires relatively little external force to keep it rolling forward. But the moment an armor-piercing shell shatters the drive sprocket and snaps the track, the physical reality of the vehicle changes entirely. When the German gunner disabled the lead Sherman on the narrow bridge, he did not just stop its forward momentum, he transformed it from a rolling vehicle into a massive, immovable steel anchor. The immediate instinct of any trailing driver in the column is to simply pull up behind the wreckage, put his own tank in low gear, and shove the dead vehicle forward and out of the way. In a civilian traffic accident, this logic works. On a battlefield, applying brute force to a paralyzed combat vehicle usually ends in disaster. When a tank track snaps under fire, it rarely falls neatly away. The heavy steel links violently bunch together. They jam tightly between the road wheels, the idler wheel, and the steel hull. Simultaneously, if the kinetic impact damages the final drive or seizes the transmission, the internal gears lock solid. Across the water, the dull, rhythmic clatter of tank tracks echoes through the valley. An American armored column is moving up. The tank is no longer resting on free-spinning wheels. It is a dead weight resting on unyielding steel wedges, grinding directly against the stone, wood, and mud of the bridge surface. To push a locked tank, a rescuing vehicle must overcome immense dynamic friction. The driver of the pushing tank drops into his lowest gear and throttles up. The engine roars, but instead of moving the wreckage, the rescuing tank's own tracks begin to slip. The steel grousers spin frantically against the slick, wet surface of the bridge, chewing up the road without transferring any forward momentum. The massive torque from the engine suddenly has nowhere to go. Within minutes, The extreme heat and mechanical stress can shatter the rescuing tank's clutch or tear its internal transmission to pieces. Now, the advancing column does not have one dead tank blocking the bridge. It has two. Even if the pushing tank manages to find enough traction, the geometry of the bridge creates another lethal problem. A tank with a severed track does not steer. If it is pushed from behind, the massive steel hull will inevitably pivot off its center of gravity. It will slide unpredictably. On a narrow span with no shoulders, this uncontrolled lateral slide can easily shove the disabled tank entirely sideways. The German gunner does not panic. He has been trained for this exact geometry. He knows the unforgiving rules of the choke point, wedging it permanently across the road boards like a steel barricade. Or worse, the pivoting wreckage can snag the front of the pushing tank, dragging both vehicles over the embankment and into the freezing water below. Standard combat tanks were simply not designed for heavy, static towing operations. They were built for forward speed, tactical maneuverability, and firing a gun. They lacked the specialized low-gear torque ratios and heavy winch systems required to drag a dead weight out of a combat zone. As the artillery spotter across the river begins calling in coordinates for a barrage, the trailing American crews know they cannot push their way out of this trap. Brute force will only multiply the wreckage. But even if they possessed the mechanical power to shove the dead Sherman, applying the weight of two grinding tanks onto the span introduces an even more terrifying threat. To clear the choke point, the attacking force had to solve a much deeper problem than just moving 30 tons of steel. They had to know exactly what the structure beneath them could hold. The river beneath the span is fast, deep, and freezing. The disabled Sherman rests heavily across the center of the structure, smoke bleeding from its engine deck. For the trailing American tank crews, the immediate human instinct is to rush forward, secure a cable, and drag their trapped comrades backward to safety. You do not shoot the fifth tank in the column. You do not shoot the third. But the surface beneath the dead tank is not solid earth. It is a suspended framework of steel girders, timber decking, and aging stone. Every bridge is a delicate equation of tension and compression. It must carry two distinct burdens. The first is the dead load, which is the immense weight of the bridge's own structural materials. The second is the live load, which is the traffic moving across the span. Before the war, this rural crossing was designed to handle a predictable rhythm of horse-drawn wagons, agricultural machinery, and light commercial trucks. It was never intended to support 30 tons of concentrated military steel resting on a single point. It was absolutely not built to support 60. If a second Sherman rolls onto the narrow span to attempt a rescue, the structural math changes violently. The weight is no longer distributed smoothly across the length of the crossing. It becomes a massive, localized concentration of heavy armor parked tightly together on the weakest section of the bridge. Furthermore, towing a locked vehicle is not a static event. When a rescuing tank drops into low gear and throttles up to break the friction of the dead tracks, it generates immense dynamic force. The grinding grousers transfer thousands of pounds of lateral shear directly into the bridge deck. They push backward against the road boards while pulling forward on the cable. This combination of extreme vertical weight and violent horizontal shearing, you let the lead Sherman roll exactly halfway across the span, where there is no shoulder, no room to turn, and no way to reverse quickly, is the exact mechanism required to tear a fragile bridge apart. The consequences of a structural failure are absolute. If the girders buckle or the stone arches collapse under the strain, the decking will not simply sag. The entire center span will give way. The disabled tank, the rescuing vehicle, and the men inside them will plunge into the river. From a tactical perspective, dropping the bridge achieves the German gunners' ultimate goal: A blocked bridge is a temporary delay. A destroyed bridge permanently severs the artery of the advance. The attacking column would be forced to halt for days, while specialized combat engineers are brought forward to construct a pontoon crossing from scratch. The momentum of the entire offensive would die in the mud. The American armor commander sitting in the tree line is trapped in a lethal paradox. He cannot leave the shattered Sherman where it is, because pre-sighted enemy artillery is seconds away from obliterating his idle column. He cannot use a standard tank to push the wreck without destroying its transmission, and he cannot safely send a heavy towing vehicle onto the span without knowing exactly how much weight the structure can withstand before it breaks. There is no time to consult a structural engineering textbook. There is no time to send a surveyor across the span with a tape measure and a slide rule. To survive the ambush and clear the choke point, then you fire. At exactly 400 meters, the gunner pulls the firing lever. The crack of the gun shatters the rain. The attacking army needed a way to translate complex structural tolerances into instant decisions, even in the middle of a firefight, through the rain. They needed an engineering language so fast and so simple that a terrified driver could read it at a glance. Look closely at the right front fender of an advancing half-track, or the steel glacis plate of a Sherman tank. Beneath the heavy splatter of mud, camouflage paint, and unit stencils, there is a distinct, high-visibility marking. It is a solid yellow circle containing a bold black number. On a standard M4 Sherman, that number is usually 30. This yellow circle is not a tactical insignia. It is the visible interface of a massive, mathematically rigid network, known as the Military Load Classification, or MLC system. In peacetime engineering, calculating a bridge's load capacity is a deliberate academic process involving blueprints, structural formulas, and time. In an armored blitz across a contested continent, time does not exist. A tank commander approaching an unfamiliar stone bridge at 20 miles per hour under the threat of artillery cannot pause to cross-reference his track's ground pressure with the age of the local masonry. He needs a binary answer: go or stop. The armor-piercing shell strikes the Sherman's right drive sprocket. The heavy steel track snaps instantly, violently unspooling into the mud. The yellow circle provided that immediate answer. However, the number inside it was not simply the vehicle's gross weight in tons. It was a highly calibrated integer. Engineers in testing grounds thousands of miles away had already calculated the tank's exact weight, its track width, the spacing of its bogies, and the intense dynamic shock it delivered to a surface when braking or accelerating. A 30-ton tank with narrow tracks and poor weight distribution might be assigned a classification of 35 to account for the concentrated shear force it generated. For this system to function on the battlefield, the equation required its second half. Hours, or sometimes just minutes before the main armored column arrived, combat engineers crawled across the targeted crossing. Working exposed, frequently under sniper or mortar fire, they rapidly measured timber thickness, steel girder spacing, and the structural integrity of stone arches. They processed this raw data through standardized field manuals to produce a matching structural classification. Before retreating, they hammered a corresponding yellow sign into the mud at the bridgehead. The resulting rule was absolute, visual, and instantaneous. If the black number painted on the tank was lower than or equal to the number on the bridgehead sign, the driver crossed without slowing down.